Okay, great. So let's get started. So today we'll be covering oscillations, simple harmonic motion. So the handout was in the email. But if you did not get it, if you did not get that email, I'm just going to send. This is a link to all the handouts, and you can at the bottom of the page download the oscillations one. So we'll be referring to that all throughout today. Yeah, I won't be screen sharing that as part of the meeting. All right. So I'll start off just by reviewing simple harmonic motion and just the basics of it. And just to start off, we just as a disclaimer, we won't be covering more advanced topics like coupled oscillations and damped oscillations, just because there's not enough time, and there's already a lot of problems with just basic simple harmonic motion. Okay, cool. So let's just do a spring. This is sort of classic example, and the idea here is that you have a wall and you attach to a mass m, and this mass m is at a position x of t. So x is a function of time, and perhaps like we've set x equals 0 to right here. Then we say that the spring has this as the relaxed length of the spring, relaxed length. Then the force on this mass is actually negative kx. So if this is the positive direction, then the force is pointing opposite towards the extension, and the magnitude is proportional to x, which is right here. So now if you write down f equals ma, what this means is that minus kx is equal to ma, we'll write a as mx double dot, because x is a function of t, and double dot means second time derivative. And then if you let omega equal root k over m, this is the so-called angular frequency, then this equation becomes x double dot plus omega squared x equals 0. So sort of solving the spring, seeing what happens to a spring boils down to solving this second order differential equation. And we won't go into the details of the math of how you do this, but I'll just tell you the final result. And the final result is that the solutions to this are a 2-parameter family, and there's multiple ways to parameterize the solutions, but the two most common ways are first like this, and second like. So as you see, in both cases, we have two free parameters. Yeah. So the idea here, sort of, this is the more intuitive physical one, where A represents the amplitude. So this you can sort of see that the motion is oscillating between plus A and minus A. Omega always is the angular frequency. So sort of this implies that the period of the motion is 2 pi over omega, because it takes 2 pi radians to complete a full cycle. And phi is a so-called phase, which is how much it's off by of just a cosine. This solution over here is sometimes easier to deal with mathematically because there's no phase, and there's sort of, you don't have to use sum and some trigonometric sum formulas. But this is useful more just when you're solving problems to maybe just write it as a linear combination of cosine and sine. But the point is both are 2-parameter families of solutions to this setup. And now the question is, why are there 2 free parameters? And the reason is that there's initial conditions. So basically, when I let go of my mass at certain x0, actually that's not all I can do. I can let go with a certain velocity v0. So if I let go at x0 with a certain velocity v0, then that will determine the rest of the motion. And that's why there's 2 parameters, because your initial position and your initial velocity are both free parameters, causing there to be a 2-parameter family of solutions. And then one more important point to touch upon here is that energy is conserved. So the spring potential energy, which we'll call U, is 1/2 kx squared. And then the kinetic energy, which we'll call capital K, is 1/2 little kx squared. So you can easily check that the total energy E equals U plus K is, oops, I made an error. this should be 1/2 mv squared, which I can write as 1/2 mx dot squared. So 1/2 kx squared. And actually, if you think about it, if you look at this, a cos omega t plus phi solution, you can see that this total energy is also equal to 1/2 ka squared, because that's when the velocity is 0 when it's at the maximum amplitude. So this is just the energy, and energy is quite useful in a lot of these problems, as you might expect. All right, so that's the classic spring example, and this is the most basic example of harmonic motion. And then let's just cover the other classical example, which is the pendulum, and then I'll comment briefly on how these sort of generalize. So then the next example is pendulum. So here what you have is you have a ceiling, and you have the vertical, and you have some bob of mass m, and let's say it's displaced by an angle theta. So like before, the variable of motion, the position variable was x, here it'll be theta. So if you have m, then you have gravity pointing downwards, mg, and you potentially have some tension force here. You can do this with forces, but personally the easiest way to do it is just by taking torques about this pivot point. And what you end up getting is that the torque on this pendulum bob about that pivot point is, if I let the length be L, then it's mg sine theta times L. This is the torque. Reason for that is, as you can see, sort of the component of mg that's relevant is the projection onto this line. And if we do L across mg, then we'll get mg sine theta times L, because sine theta is the angle between the L vector and mg vector. And then the angular acceleration, since we're sort of implicitly, so actually, let me revise what I just said. I'm going to say that the torque is equal to negative mg sine theta times L. The reason for this is that we're taking theta positive to be in this direction, the way we define theta, and therefore, since the torque is trying to pull this thing down, it will have a negative sign. And then obviously the angular acceleration is theta double dot. This is angular acceleration. And the moment of inertia is ml squared. So then our equation becomes negative mg sine theta times L equals ml squared times theta double dot. So this then becomes theta double dot plus g over L sine theta equals 0. So this is our new differential equation. If you compare it to what we had above, it was x double dot plus constant times x is constant. Here it's theta double dot plus g over L sine theta is constant. But of course, as you might already know, in the pendulum, we assume that oscillations are small. And in that case, we can use the small angle approximation, which states that sine theta is approximately theta in radians, of course. And then this differential equation just becomes the usual harmonic differential equation. And then we find that the solutions are the same form as before. So theta of t is some theta 0 cos. So here again, the angular frequency is root g over L. Okay, so that's the case of the pendulum. And let me just sort of say in general, when you have oscillations, small oscillations, especially physically, you have small oscillations. Let's say the parameter, the position parameter is some p. So p is either x, that was in our spring example, theta in our example just now, and usually it'll be one of x or theta, but in different contexts. Then if you can write the restoring force, you can write it in terms, it should be proportional to p. So the restoring force obviously will be something, but when you take p to be small, then you can usually write the restoring force as for some constant k. And then the acceleration is obviously, so then by your F equals ma equation, you get something like this. And this will give you some more harmonic motion. Obviously, this is sort of like vague because there's no physical setup, but you'll see in the problems, there'll be a couple of problems where this will be important, where you sort of try to reduce to a differential equation like this, and then just cite the harmonic solution. And again, the period, just I already mentioned this before, but if you have so sort of the angular frequency is x, then the period is 2 pi over omega. Okay, great. So that that sort of just covers what I wanted to say before, but most of the sort of problem solving ideas will be coming through the problems. Okay, great. So let's get started with the problems. And again, please open the handout, because I'm not going to be able to write the prompts here or screen share them. So I'm going to be assuming that you're able to follow in the handout. I sent the link in the chat. I'll just send it once again in case anybody joined afterwards. Go here, download the physics circle oscillations at the very bottom of the page, so that, excuse me, we can get started. Also, unfortunately, we do not have the ability to do polling today. So because of that, I'll just give like a minute for you to think about it, and then I'll go over the solution without the poll data, unfortunately. All right. So let's start with problem 1. So this is F equals ma. Okay, before I do that, let me say, are there any questions about what we covered up to this point? And feel free to unmute and just ask your question. Okay, it looks like there's no questions about what we talked about so far. So in that case, we'll just get started with the problem. All right. Yeah. So the question basically is that you have an object of mass m, and it's hung on a vertical spring constant k, and then it has period of, so it's oscillating up and down, and period t0. Now the spring is cut in half, it's sort of cut in half, and you just take 1/2 of the spring, so sort of this half of the spring, and attach it to a frictionless inclined plane. So you take this, and now it oscillates back and forth, no friction. So find the period here. This is sort of the question. So this question is going to be illustrating 2 principles about simple harmonic motion. The first one is sort of that these external forces like gravity, like hanging a spring down or doing it horizontally where there's no gravity, will actually produce the same period and essentially the same motion. And you might have already seen this, but it's sort of the idea of when you hang a spring in a gravitational situation, sort of what happens is the spring extends a bit, and it extends exactly such that mg equals kx naught. So the spring extends by x naught, so that this equation is satisfied for force balance. And then you can see that the force due to the spring, the force on the spring later on is if we take this direction to be positive, is negative kx plus mg, which is equal to negative kx plus kx naught, which is equal to negative kx minus x naught. So what this means is that there's just oscillation about this new equilibrium x naught. And it's as if there was no gravity, because we sort of canceled it out and wrote it like this. So simple harmonic motion in vertical setting, and again in this horizontal setting, you can do a similar calculation. You'll see that there's no effect to the period. It's just the same motion. So again, the period will just be, in this case, for a spring, it's always 2 pi root m over k. And that will be the same whether it's vertical or on a plane. So the plane is just sort of a red herring. But anyway, so the question is now, how does the mass change and how does the spring constant change? So obviously the mass is not changing. They told us that at the start. So the question is, how is the spring constant changing? And indeed, we're cutting the spring in half. So this is the second important fact, which is not really a harmonic motion fact, but it's a fact that you will see a lot on the F equals ma, which they like to talk about, which is if you cut a spring in half, this is a principle. Cutting a spring in half doubles its spring constant. So cutting a spring in half doubles its spring constant. The reason for this is, so let me just go over the reason for this. And the idea is that if you have a spring made up of two halves, like this, and if you extend the entire, so this is the, let's say this is relaxed. This is the pivot. This is relaxed. Then we extend it by x. So now this is extended by x. Then what's going to happen is that each piece will extend by x over 2. Each piece will extend by x over 2. And what that means is that if we have the final state, right here, then this has been the sort of the x over 2 extension for this half spring. And obviously on this sort of end right here, the only force being felt is the force from this half spring, because that's the only attachment right there. So if the spring has been extended by x over 2, then sort of if the spring constant here is k prime, then k prime times x over 2 has to be the total force on this. But we already know from if we treat the whole thing as one spring, it should just be equal to kx, just because that's what the spring constant means. And then this implies that k prime is 2k. All right, but with this observation, with this problem, essentially what's happening is m is staying the same. I'm just going to m. Spring constant is being doubled. So this means that the period is going to be going to t over root 2. So it will be d. Okay, somebody mentioned in the chat that the overall spring constant is harmonic sum. Indeed, that is correct. So basically what's being said is if you have so I'm not going to go into the math of that. I think what I want to emphasize is you can do a similar calculation as what I just did here. If you have length 1 and length 2, you can argue how much they're going to be scaled proportionally. You can do a similar argument and you can figure out the new spring constant. The sort of most common cases when you cut it in half, then the spring constant doubles. Okay, I'm having a couple questions. Let me first cover about this argument in more clarity. So what's happening here is we have sort of two springs joined together of equal length. Somebody unmute. Oh, I'm assuming that was by mistake. Okay. Sort of have these two halves right here. And what's happening is that when you extend the overall spring by x, then each spring will be extended by x over 2, proportional to its length. So the total extension is x. And that means that if each spring that the total spring is made up of has spring constant k prime, then each one is providing restoring force k prime times x over 2. So the restoring force over here is k prime times x over 2. Now this has to be equal to kx because we know if the overall spring constant of the spring is k, what that means is that the restoring force is kx. That's sort of from the definition of k. If I'm saying k is the overall spring constant of this entire spring, then that means that it should be kx over 2. Sorry, that means the kx should be the restoring force. We already know it's k prime times x over 2 because of the setup of joining two springs. Therefore, k prime times x over 2 is equal to kx, which means k is 1/2 of k prime, or k prime is 2k. So this sort of justifies why cutting a spring in half doubles the spring constant. Second question I got was, where did the t's to t over root 2 come from? Great question. So the period of a spring is 2 pi root m over k. This was covered before in the theory section. And this is the period of a spring. Okay, I'll answer that question as well. So assuming that there's no interaction from gravity, the idea is that if m is staying the same as the problem suggests, k is being doubled because we cut the spring constant in half. then you can see in this expression right here, 2 pi root m over k, if you keep m constant, double k, t will go to t over root 2. Okay, I hope that answers that question. Let me answer the next question, which is the mass of the block doesn't change on the inclined plane, but the gravitational force would because it's an angle. Why does that not affect the period? Great question. So essentially what's happening is that if you think about looking at the motion parallel to the plane, what you do is you essentially have an extra g sine theta force in this direction. This is analogous. This is completely analogous to the case where you have just an extra g force in this direction. So sort of it's no different. Just there's a g sine theta force and there's a g force here, and sort of what this g force does, like I said here, is it just shifts down the equilibrium point. But once the equilibrium point is shifted down, the oscillations above that equilibrium point still have spring constant k. So what this equation demonstrates, the force is still negative k times x naught, if x naught is the equilibrium point. Then because of that, the oscillations are still having angular frequency root k over m, and therefore period 2 pi root m over k. So the short answer to your question is extra constant forces like gravity will only change the equilibrium point location, but they will not change the period. Okay. Somebody's asking 2 pi square root m net over k net for all cases. Yes, but I'm sort of not going to, I wouldn't say like that, because really this only holds in the case where you have a spring and a mass attached to it. Like, I'm not sure what you mean by k net and m net. Like, if you have multiple masses and you have multiple springs, then the system is more complicated. If there's just one spring attached to a mass, and when I say one spring, it's okay for that spring to be made up of multiple springs because we're still viewing this entire thing at the end of the day as one final spring. So it's not, I don't think it's accurate to say that if you have multiple masses and multiple springs, it's 2 pi root m net over k net. Just well, you have to specify more detail to the setup if you have multiple masses and springs. That's, I guess, what I'll say about that. Okay, so hopefully I answered all the questions about this. Looks like we have a lot of questions, which is good. So let me just also, I apologize, I didn't give people time to think about this one before. I'll do that for the next one. Let me just, for another minute, does anybody have any more questions about this problem and how we did it? And again, to recap, sort of, in my opinion, the two main ideas were, one, that the external gravitational force will only affect the equilibrium point, but will not affect the period of the oscillation. That's the first major concept. The second major concept is that cutting a spring in half doubles a spring constant. Those are the two main concepts. And then combined with the period formula for a spring, that solves the problem. Okay, so let me just give a minute where people can ask questions. All right. Okay, so if there aren't any questions, then let's go on to the next question. So the next question is a bit different flavor. It's not springs, it's related to pendulums. And that's actually not even that related to simple harmonic motion. I just put it in there because it's sort of a classic pendulum question and analyzing the motion of a pendulum. It's not super relevant to our lecture today, but I'll just quickly go over it just because it's related to pendulums, and pendulums are related to oscillations. So F equals MA 2015-3. Again, please look at the Prom statement in the handout. And let me just give 1 minute for everybody to think about this problem, and then I'll go over it. So yeah, please take your time. And also, if you have any questions about the previous one, please also ask those. All right. So hopefully everybody's got a chance to think about this question. And let me go over the solution to it. So the answer is actually D. This one's a bit of a tricky question, so I'm sure people might have got the wrong answer, and that's okay. We're going to go over how to do this question. So the answer is D. And the reason for this is the following. So we sort of have a pendulum. It's swinging currently upwards as of now. All right. So there are two ways to do this question, both of which give the same answer. So the first way is to just use forces. Just analyze what forces there are on this and just see what that gives us. So the forces on this object are mg downward and tension pointing inward. And if you think about how these add, I see. Okay, so I take back what I said. This is not enough to determine the answer, but it's enough to narrow it down to two options. So what's going to happen is we see that first of all, it's going to have a, so if we sort of split into components in this direction and in this direction, let me call this y and call this x, it'll have a positive x component. But we can't really say anything about y. We can't say whether mg or the component of mg or the component of t is larger or not, but we know it has a positive x component. And that's actually enough to eliminate choices A, B, and C. So this itself eliminates A, B, and C. And again, sorry, I forgot to mention this. The idea is that the net force is in the same direction as the acceleration due to Newton's second law. This eliminates A, B, and C, and we're left with D and E. So the question now becomes, is the y force, is it positive or negative? And in fact, perhaps a better notation would be to call this radial and tangential, which is the standard notion for these directions. All right. So the question now becomes reduced is, so as you can see, this eliminates A, B, and C because we have a positive tangential component. So the idea is that there's a positive tangential component to the force. As you can see, this mg will split up like this and like this. So the tangential component of the net force points in this direction. And you can see that in A, B, and C, A has no tangential component, and B and C have the wrong direction of tangential component. So it's either D or E. Okay. So the question now becomes, is the radial acceleration inward or outward? Now, this is the key sort of observation from circular motion. And the observation from circular motion is that if an object is moving in a circle, regardless of whether it's uniform velocity or not, then there's always a centripetal acceleration of v squared by r. R is the radius. This is just a general fact about circular motion. It's always v squared by r. And there's also going to be a tangential acceleration. This is a centripetal. And there's going to be a tangential acceleration, which depends on how v is changing, but there's always v squared by r pointing inward. So again, in this case, the object is moving with velocity v, and therefore there must be an inward radial acceleration. So there must be an inward radial acceleration, and as you can see, only D has an inward radial acceleration. E has outward radial acceleration, which doesn't make sense because in circular motion, and again, the pendulum's trajectory is an arc of a circle. There must be a pointing inward centripetal acceleration. So therefore, the answer is D. So again, to recap, tangential removes A, B, and C, and then analysis of radial tells us it's to D. Okay. So any questions about this? Okay, looks like no questions, so we'll move on to the next problem. Okay, so this is F equals MA 2016. So for this one, since it was an entire page, I just took the page from the F equals ma. So if you go to the last page of this document, you can see that excerpt from the F equals ma for 2014 problem 14 and 15. So maybe this one is a bit longer, so I'll give everybody 2 minutes to try it, and then we'll talk about it. And again, if you have any questions about the previous ones, then please ask those as well. All right. So I think I've given some time to think about this question. So maybe I'll go over 14, and we'll give some more time to think about 15. So let's go over 14 first. So again, the setup of this question is you have a rod. So the original setup before we make any modifications is you have a rod of length L. It's a uniform rod, so we'll be using circular motion, moment of inertia type things here. And then we have this huge, we have this post, and this is a huge length of L. So the spring is sort of stretched out by a really large length, and they've told us that L is much, much greater than L. And the question is, when this thing is rotated slightly, it oscillates with frequency F. So let's first analyze this situation, then we'll analyze the other situation so we can compare. So in this situation, what happens is it will illustrate the principle of general harmonic motion, where you have to get the differential equation yourself and then just cite the harmonic motion equation to get the angular velocity, angular frequency. So let me demonstrate that here. So what happens here is that the oscillation is in the angle of the rod. In the angle of the rod. This angle is the thing that's oscillating. Now, the force, the force on this rod, since capital L is much, much larger than small l, what we can essentially say is that L went, the sort of extension of the spring went from L to L plus little l sine theta. Just because this amount got added. Obviously, it's not exactly correct because the geometry doesn't work out, but since it's very, very far away, we can make this approximation. Therefore, the force coming down is equal to k L sine theta. And therefore, the torque on this object about this pivot, the torque is KL squared sine theta. All right. Now the torque is KL squared sine theta. And then if we use torque equals I alpha, so we say KL squared sine theta. And I'll just let the moment of inertia be I. Obviously, the moment of inertia is 1/3 ml squared, but we actually don't need that. We'll just call it I. And then alpha is equal to negative theta double dot. Sort of there's always a negative sign because the torque is trying to reduce theta, and theta double dot is sort of positive when theta is increasing. That's why there's an overall negative sign. Anyways, but the point is this implies that theta double dot plus KL squared over I sine theta is 0. And then if we approximate sine theta to be theta, then we find that the angular frequency is, and the regular frequency, this is something I forgot to mention, is always just 2 pi times the angular frequency. So this is the regular frequency in this setup. This is the value of f. So again, this is the solution in the normal setting. Now, if we do problem 14, and the spring has now moved to half the distance. So in fact, the only change is that now, if the spring is now at half the distance, and this increased by theta, then L now only went to L plus L over 2 sine theta. So the force is now KL over 2 sine theta. And again, the torque is now only the force times L over 2 because the lever arm is at L over 2. The torque is now KL squared over 4 sine theta. And then the I alpha is exactly the same. So if you see what's going on in our equation, I'll just skip some of the algebra, but what you can see is that the equation now becomes, and again, if we approximate sine theta to theta, this tells us that the omega is the square root of that coefficient, which we can see is 1/2 of the original omega. So the sort of the, if you call this the original, so the new frequency is 1/2 of the original frequency. So the answer to this problem is A. Because we saw from the equation that the differential equation that we got a factor of 4 in the coefficient, and the frequency is the square root of that coefficient in the differential equation, and it halved. Someone's asking me, is there a way to do this without the equation? I do not think so. I mean, there might be other ways to phrase it where you just bypass doing the equation. Yeah, actually, I would say there's no way to do this without the equation. You have to set up the force equation. You have to write it as a simple harmonic equation, which is again of the form theta double dot plus something times theta is equal to 0. An equation of this form will become harmonic oscillation with frequency omega. So the only way to do this question is to write the equation. So now let's try problem 15. Same setup, but instead of moving it now to half, we moved it sort of moved it to horizontal. By the way, right now, please please try Prom 15. And also, if you have any questions about Prom 14, also ask those. Okay, let's go over Prom 15. So what's happening in this one now is it's sort of a little bit of a different setup. Again, the same rod, but now the post is very far away and it's L. Sorry. So I'm mistaken. This is L plus L. So the spring already has a force of KL pointing in this direction. And now we sort of modulate the angle of the rod and see what happens. So the observation here is that when you modulate by theta, to first order, this length remains L plus L. And the modification to it is something on the order of theta. So it's about L plus L, but there's maybe some sine theta factor which changes its value. The point I'm trying to make here is that the angle anyways between this KL, this force, and theta is already on the order of theta. So then the entire torque on this thing is F sine theta. That this is KL plus maybe some theta, some theta modification proportional to theta times sine theta, which means that the overall torque is KL sine theta plus order of theta squared modification. So actually, my point is that in this problem, the amount that the spring changes its length by is actually not relevant, because since the torque angle is so small that the smallness of the restoring force is coming from the angle, and this extra modification to the length will not affect the torque on this rod at order theta, which is all we care about since we're approximating to first order in theta. So in fact, the torque is essentially negative KL sine theta, as it happens to be in the setup. And coincidentally, that's the same exact oops, my bad. Torque is F sine theta times L. I dropped the L in there. My bad. Times L KL squared. And as it happens to be, that's the exact same torque we got for the problem for the original setup. They came out from completely different scenarios. It came out here in a completely different way than it came out here. And sort of it came out here in a sort of cheap way because they artificially made the spring stretched by a distance of little l, which means that they artificially made the force k little l, so it's the same as before. But anyways, the torque is the same as before, so the equation is exactly the same as before. So it turns out that the governing differential equation is identical mathematically, which means that the frequency in Prom 15 will remain the same. So it's C. So again, I want to highlight this is the poster example of a problem where you have to write down the differential equation, and then that will guide you to the frequency. Yeah, this is the poster example of that sort of general principle where you have to write down the differential equation and then see where that leads you. So I think this was kind of a beefy question. So maybe I'll give everybody a minute to think about it and ask any questions that they want to about any of these problems, 14 or 15, or the original setup as well. So yeah, please ask any questions you have. Somebody has pointed out an error that I made, and they're absolutely right. This is just a little silly mistake I made. The frequency needs to be 1/2 pi times omega. I apologize for that. That's correct. Yeah. Okay. 2 people independently pointed it out to me, and yes, you are both right. The frequency is 1/2 pi times the angular frequency. Cool. So let's give everybody 30 more seconds to ask any questions, and then we'll move on to the next problem. All right, looks like no our questions are being asked about this one, so let's move on to the next problem. So F equals MA 2017 number 2. In my opinion, this is one of the trickier F equals MA problems that have appeared recently. So yeah, so this problem is quite tricky, but it illustrates a couple of important concepts. So let me just give everybody 30 seconds to a minute to think about this one, and then we'll go over it. Okay. So for this question, what we have is we have two different situations. One is where we have a box of mass m, and let's say it's on the ground, held there on the ground, and we have a spring of mass, spring m, and this guy is going to be oscillating up and down. So we have some omega here, and we have another scenario, which is we have the box of mass m, we have the spring here, and then this this is all in free fall, and there's some oscillation. So how does the angular frequency change from case to case? So based on what I told you before about the equilibrium point shifting down, one might think that the angular frequency is the same in both cases, because it's the same mass oscillating, just the same mass little m oscillating, and it should just be root k over m. It should just be, so obviously in this case it's just root k over m because it's a classic setup. But in this case, similarly, when it's falling down, it should be the same thing. So a lot of people might answer A for this question because of that principle of the equilibrium point shifting down, but the oscillation not changing. However, the key in this problem is to realize that that principle does not apply here, and there's actually something more subtle going on here, which yeah, somebody pointed it out, which is going to change the answer here. So the point here is that yes, there's two ways to think about this. Let me actually reference frame is not isn't inertial though. So actually the reference frame isn't inertial is I don't think will cause a problem here, unless I'm very mistaken. So I'll explain what the issue is. I don't think it's equivalent to reference frame not being inertial. So obviously, again, in the case where it's on the ground, as we saw before, it's 2 pi root k, it's root k over m, the angular frequency. Nothing funny going on here. when it's falling down, what's going to be happening is that the box will also be oscillating along with the little mass. Right. So you can interpret your answer like that. Okay. So the box will be oscillating with a little mass, and therefore the oscillation will not just include the little mass, but it will include the box as well. And that is going to change the motion and the change that is going to change the angular frequency. So the point is we're actually going to transfer into a so-called non-inertial frame, which is going to be falling down. We're going to be falling. We'll transfer into the frame. Transfer into frame falling at G. So we'll actually transfer into this non-inertial frame, which is falling along with this system. And in that frame, it's as if these guys are just in vacuum. So this is sort of like I think this might be called Einstein's principle, but I'm not really sure. Is that if you're in free fall, then it's as if you're just in free space with no gravity. So the problem reduces to if these are just in space, then what's the oscillation period? And in fact, when I say in space, you might think about, let's say, the International Space Station. So let's say take this International Space Station, see what happens there. But in fact, the reason that the International Space Station is so-called no gravity is for the exact same reason that this is no gravity, because actually the International Space Station is constantly falling with acceleration g, with centripetal acceleration g. And since it's constantly falling, but now it's in a circular orbit, in that frame, it's as if there's no gravitational acceleration. So truly this problem is equivalent to imagining that the system is in space and there's no gravity and you're just having these guys oscillate in free space. So now the question becomes, if I have box of mass m and object of little mass m, and these guys are oscillating in free space, then what is the frequency? Now, the structure of the box, as you can see, the structure of the box really doesn't matter. And we can, let me see if what I'm about to say is correct. Yeah, this is correct. We can sort of just imagine it as a point mass m and a little mass m right here. And imagine these two are, we just imagine pulling them apart and imagine oscillating them. And what is the frequency of oscillation here? Now, people probably have seen this before. What ends up happening is that it's root k over the so-called reduced mass, mu, where this reduced mass is so-called harmonic sum of these two masses. And if you already know this formula for this situation, that it's just this is the frequency, then you'll find that the answer is B, because this is always less than m. So the mass increased, the so-called effective mass increased, the k stayed the same, so therefore the frequency went up and it's B. But sort of this formula is kind of obscure. I'm just going to derive it right now because I think it's really important to see how this works. And then once you have this formula, then the answer is obviously B. So the idea behind this is that so let's say the relaxed length is L. Then imagine it coming out a bit. The key idea is that the center of mass stays fixed. So the center of mass was originally here, maybe because capital M was heavier. The center of mass still remains here. So what that means is that if this guy moved out by x compared to the center of mass, then by center of mass conservation, excuse me, this must have moved out by little m over m times x. And sort of this is set up such that the center of mass remains at that point. So now in this case, what ends up happening is that the overall restoring force, let's say on little m, is now k times x plus. The restoring force is k times x. And then this is equal to negative little mx double dot. So if you see this becomes x double dot plus little m times m. So then the omega is simply root k times This is the angular frequency, and this is exactly the same as this formula if you see the math. And then again, since you can just analyze that this form of this omega is always greater than the original root k over m omega. All right. So this question had quite a bit sort of realizing that the situations are different, then realizing that the falling is exactly equivalent to free space, and then knowing how to deal with two-body oscillation with a spring. Any questions about any of this? All right. I'll just give everybody a little bit more time. So any questions about the falling into a frame, and that's equivalent to just free space? Any questions about this sort of two-body oscillation? This two-body oscillation shows up quite a bit, so knowing how to deal with it is pretty important. And sort of the main idea behind the two-body oscillation is that the center of mass stays fixed, and that allows you to do the analysis. All right. So it looks like nobody has any questions about this. Nobody's asking any questions about this, I guess. So let's move on to the next question. So we got the request in our feedback form to cover a few more harder questions. So what I'll do is sort of proms 5 and 6 are both good practice proms with similar concepts we've already covered. So I think in that sense, I'm not going to cover 5 and 6 because 5 again is sort of the half spring concept, cutting a spring in half, and also sort of writing the differential equation concept will be applied in Prom 5, which is F equals m in 2018, A Prom 11. And for Prom 6, which is from Morin, the concept again is exactly write down the torque, write down the equation, the differential equation, and just find out what that find out what the constant factor in that equation is and take its square root to get the frequency. So Prom 5 and 6 both use ideas we've already covered. And in that, for that reason, I won't cover them right now. And instead, we'll cover 7 and 8, which are two sort of very tricky, harder oscillation questions. So we'll cover Prom 7 first. This is a very nice classic problem, which is the following. So we have a spring oscillating with spring constant k, so this is very familiar, and it has amplitude a. So the maximum extension is a in our oscillation. All right. Now, over a very long period of time, and the period of time is at a much, the sort of period of time is like maybe a factor of a million more than the period of the oscillation. So if the oscillation is moving like this, then maybe over like a year, this thing will, the spring constant will slowly decay from k to k over 2. So maybe you've set up like a perpetual oscillator, but the spring constant is decaying from k to k over 2 because the spring is getting less tight over time. This will change the motion somehow. It will change the motion of the spring. So how does this, what will be the final amplitude? What is A goes to what if the spring constant decayed? So this is the question that is posed. Maybe I'll give everybody a minute to think about it, but there's no way anybody can solve this question in a minute unless they've already seen the idea before. And I'll just give everybody a minute so they can just get acquainted with the question and maybe ask any questions about the setup, and then we'll go over the solution to this one. So is the setup clear to everybody how the spring constant is decaying, and it's decaying at a rate much, much, much slower than the oscillation itself? And then over time, sort of at any given time, the oscillation looks really perfect, but over this whole year, sort of the oscillation may decay because the spring constant is decaying and the amplitude will change. So that's the process. We're trying to analyze that. Okay. So if nobody has any questions about the setup, then we'll start going into the solution. So solution. So the main idea is to analyze energy losses. So the reason, let me tell you the reason that the amplitude will change is because at any given point of time, at any given point of time, you're oscillating, and let's say the spring constant just instantaneously decays by a small amount, and you have some potential energy stored in the spring. So if the spring is stretched out and the spring just decays at that moment, then that potential energy will be lost because it went from 1/2 kx squared to 1/2 smaller k times x squared. So you're losing energy that way. And over this long time, you're losing a lot of energy through that process, and that will cause the system to change. Okay, so that's the main idea. And let's go over the details of this process. So the idea is to analyze one single oscillation. So let's analyze one oscillation. Back and forth, plus a to minus a and back. So 2 pi radians. Since I said that the decaying is much, much slower than the oscillation, we can ignore, during one single oscillation, the amplitude is not really changing by much, and we can assume it's constant for one entire oscillation. But what's happening is that sort of the spring constant is constantly decaying. So there's multiple phases to this motion. So one is when it's at plus a, v is 0. Then this is when x is 0 and v is v max. Then there's x equals minus a, v is 0, and so on. You have situations like this. And one thing to realize is if the spring constant decays a little bit in this situation, then a lot of energy will be lost because all the energy right now is stored as spring potential energy. So a lot of energy will be lost. If the spring decays at this state, and no energy is lost because the spring is not storing any energy right now. All the energy is stored in the kinetic energy of the mass. And in this situation, again, the energy is stored in the spring, so we'll lose energy. So it's not clear exactly how much you will lose energy because it could be happening all these different times. But since this process is happening over a long period of time, what we can assume is that on average, it'll happen on average in all situations an equal number of times. Equivalently, we can say over the entire oscillation, the spring constant is decaying at a constant rate. So what this means is that if the spring constant is decaying at a rate r, what this means is that after time t, it drops by RT, then we have the following. So we have x of t is equal to, just for simplicity, let's just say it's a cos omega t. Omega is root k over m. Then at any point in time, sort of the energy is going down from to 1/2 k minus so in time dt, energy loss is so then the idea is that over an entire oscillation, So if we let the period be t equals 2 pi root m over k, the energy loss over full oscillation, so full period, is of 1/2 Rx squared dt, which is sort of, you can work out this integral. It's 1/2 R integral 1/2 RA squared integral 0 t squared dt. And if you work this out, what you will end up getting is this is 1/2 RA squared times t over 2. The way I got this so fast is essentially what this, the average value of cosine squared is 1/2. So that way it's just t over 2. But you could also just work out the integral using normal methods, and you should get t over 2. So this is 1/4 RT a squared. So essentially what this is, so what we've got now is that in one period t, we lose energy. Now at any sort of period in time, now our time, let's shift our time scale to the sort of global year-long time scale. What is this slowly decaying? The overall energy is always 1/2 Ka squared. So what this is saying is that in one period, and now this one period can be viewed as a very small amount of time, because this period, this is a very small amount of time compared to this year-long process of this spring constant decaying. What we're essentially saying is that the change in energy per time is 1/4 RA squared. If we now take our sort of time scale to be very large. So this means is that dE dt is equal to negative 1/4 RA squared. And then if we now we just see what this gives is that dE dt is equal to 1/2. Now if we just use the product rule, this is a squared dk dt plus k times 2a dA dt. And dk dt is equal to negative r by definition. And we're told that this is equal to, and then we're given that this is equal to negative 1/4 RA squared based on our previous work. So what we have is negative 1/2 RA squared plus Ka dA dt So Ka dA dt is I think I've made a mistake in my calculation somewhere. Sorry, just give me a sec. Oh, never mind. Sorry, my bad. No mistake. I don't know why I thought that. So this is 1/4 RA squared. So what I can write this is that Ka dA dt is equal to 1/4 dk dt a squared negative. Because r is negative dk dt. So the dt will cancel out. And what this now tells us is that dA over A is equal to negative 1/4 dk over k. And if we integrate this, what this tells us that log A is equal to negative 1/4 log k plus a constant. So what this tells us is that A times k to the 1/4 is equal to a constant. So what this implies is that if k goes to k over 2, then the amplitude actually increases, and it increases to 4th root of 2 times A. So the final answer is 4th root of 2 times A. This was kind of a long and tricky solution. But it sort of tells us important principles about energy loss. So if you have energy loss in the system, then we're sort of calculating how much energy is lost over an entire cycle. So I know this was quite kind of fast and hard, but does anybody have any questions about the setup and sort of what our general approach was to solve this problem? All right. Yeah. Cool. So I think probably now I have either the option of covering the other hard question, which is problem 8, or have the option of going over 5 and 6, which are the F equals ma and the Morin question, which are illustrating principles we saw before. What preference do people have? Sort of the other harder question is analyzing a non-harmonic oscillation. So it's an oscillation which looks harmonic, but it ends up being non-harmonic, and sort of dealing with that. Okay, so I'm getting conflicting answers. Okay, I think probably what I'll do is I'll cover Prom 6 and Prom 8. So Prom 5 I think is a good practice problem that people can do on their own, and then I'll cover Prom 6, and then after that we can start on Prom 8, and if we have time, then finish it. So Prom 6 is F equals, sorry, this is Morin 10.13. Okay, so the setup here is that we have a uniform cylinder right here of mass m. So its moment of inertia, of course, is 1/2 mr squared. The radius is r. And we have a spring attached here. Yeah, and the spring is currently at its relaxed length. So now the question is, if this object rolls on the ground, then how does that rolls without slipping, and what is the frequency of oscillation? So why doesn't it? I'll give maybe a minute for everybody to try this question, and then we'll go over the solution. All right. So the idea for this question is that since it's oscillating about, it's rolling without slipping, we can sort of view it as just oscillation about the contact point. If we can sort of just imagine it oscillating about the contact point like that. So in that sense, it's actually almost exactly the same problem as the F equals MA 2016 problem 14. So if you all can look at that problem again on the last page of the handout, this problem is almost exactly the same as that problem. Because what's happening is we have a sort of pivot point right here, sort of fake pivot point, because it's rolling without slipping. And we have a spring attached here, which is going to be providing a restoring force. And we'll have an oscillation. So the moment of inertia about the pivot was something we need to find first. By parallel axis theorem, it's 1/2 mr squared plus mr squared, 3/2 mr squared. This is the relevant moment of inertia. And now if this if sort of this rotates by an this sort of not a very good picture, but if it rotates by an angle theta, then we can see that the spring moved by. The spring got extended by 2r sine theta, because sort of this distance is 2r. And if you rotate by theta, then you get extra 2r sine theta in the spring. So the force from the spring is equal to 2r sine theta times k. So torque due to the spring is k times 2r sine theta times 2r. And the angular, and then this is equal to negative 3/2 mr squared theta double dot. And then I'm going to approximate sine theta as theta. And what we end up getting is that 4r squared k sine theta plus 3/2 mr squared theta double dot is 0. This implies that theta double dot plus 8/3 k over m equals 0 theta, if we approximate sine theta to be about theta. So then the angular frequency is 8/3 k over m. So any questions about this one? All right. In that case, we'll just cover problem 8. Okay, so I guess we were supposed to stop at 11:20, so I'm not sure if we have time to cover problem 8. So maybe I'll just sketch the idea for problem 8, and then we can stop after that. This is problem 8. This is from the reference puzzling physics problems, which I've referred to in the handout. So the idea is that you have two this is a bad drawing. We have a mass here, and these are two unstretched springs, so strings at the relaxed length. Then we sort of displace this mass upward by a bit, and then let this thing oscillate, and we want to find essentially the period. We want to it turns out in this case the period will be a function of the amplitude, which is what the problem is telling us, and we're asked to find what that is. Recall in simple harmonic motion, the period did not depend on the amplitude. So if I let go at a certain stretch, the period is still 2 pi root m over k, no matter how far I release it from. But this problem will turn out to be not simple harmonic motion, so that property won't hold. So let's see what happens here. So if we extend it out by x, these are still L, and the spring's length is L squared plus x squared. So the force is now, restoring force is k times, and since we're assuming x is much less than L, so small oscillations, we can use Taylor approximation on this. And this is approximately equal to KL times 1/2 x squared over L squared is equal to. The force is quadratic, and then if we take the two components of it, because they only their vertical component matters, the final restoring force, F restoring, is equal to negative 2 times 1/2 k over L x squared times sine theta. And we can approximate sine theta as just tan theta, which is x over L. So this is about so we've actually got a problem where now mx double dot is equal to negative k over L squared times x cubed. So this is actually simple harmonic oscillation, except we replaced x with x cubed. And the question now becomes to solve this case and figure out the period. So I'm not going to cover I'm not going to tell how that's done, but again, the hint is to use sort of use energy, quote, energy considerations to find v as a function of x. And once you found v as a function of x, you can do some calculus tricks to find the period. That's sort of the sketch for this problem. But the sort of what I want to highlight is that in situations like this, you can get non-harmonic oscillation. So it's not always the case that when you do small oscillations, you'll always get harmonic equation. There are cases like this where if you try to do small oscillations, you end up getting a non-harmonic oscillation equation like this, where instead of x, you have x cubed. That was the main thing I wanted to highlight in this problem. And actually solving this is some mathematical manipulation, which is not easy, but there's not much physical insight there. Okay, cool. So thanks for coming, and we'll see you next week as part of the next week's physics circle. And the recording will be uploaded for this class, and at some point the solutions will also be sent out for this. So yeah, that completes what we just. So that completes the lesson today, and we'll see you all next week. Bye.